Hello friends, welcome you all to the 48th lecture on function analysis and its applications. In this lecture, we will discuss the normal operators. This is the content of today's lecture, that is normal operators. Normal operators definition. Let H be a Hilbert space and let T belonging to BH. BH is the set of all bounded linear transformation on H. And T star be the adjoint of T, then T is said to be normal if T star is equal to T star T. That is, T is said to be normal if it commutes with its adjoint. From the above definition, we get the following properties. First, every self-adjoint operator is normal. Since T is self-adjoint, we have T is equal to T star. Hence, T star equal to T. Why? Because T star is T. And T can be written as T star. So, this is T star T we can write. Hence, T star equal to T star T. Therefore, every self-adjoint operator is normal. So that T is normal operator. Noting point. A normal operator need not be self-adjoint as shown by the following example. Here we have proved every self-adjoint operator is normal, but converse is not true in general. So, by this example, we can prove it. Let H be any Hilbert space and I, that is identity operator, such that H to H, take T is equal to 2I. This I is iota, capital I is identity operator. Then T star equal to conjugate complex of 2I into I star, because we know that alpha T star equal to alpha bar T star. So, taking star of this, that is adjoint of this operator, then we have T star is equal to conjugate complex of 2I into I star. That is 2I bar. I bar, that is minus I. So, it will be minus 2 iota into I. So that T star equal to T star T is equal to 4I. Okay. If we multiply T and T star, we have 4 into identity operator. Hence, T is normal operator on H, but T not equal to T star. That is, T is not self-adjoint. So, we have every self-adjoint operator is normal, but converse is not true always. Second property, if T belonging to BH is normal, then T star is normal. Why? We know that if T star is adjoint of T belonging to BH, then T double star is equal to T. Since T is normal, T star is equal to T star T. Hence, for T star, this T star into star of T star, that is T star into T double star. T double star is T. This can be written as T star T, and T is normal, that is T star T can be written as Tt star. Again we can write by this T double star, and T double star can be written as star of T star. That is, this one is star of T star into T star. Okay, so T star into star of T star equal to star of T star into T star. That is, T star is normal. Okay, hence if T is bounded linear operator is normal, then T star is also normal. Next theorem. The limit n of any convergent sequence nk of normal operators is normal. Proof. Now norm of nk star minus n star equal to norm of the star of nk minus n, because we know that T1 plus T2 star is equal to T1 star plus T2 star. Okay, so this can be written as star of nk minus n by this property. Okay, and also we know that norm T star is equal to norm T. This is not norm T star. So this can be written as norm nk minus n. Okay, where nk converges to n, that is norm of nk minus n converges to 0. Okay, so since nk converges to n as k tend to infinity, from this step we get norm nk star minus n star converges to 0, that is nk star converges to n star. To prove n is normal, so we establish this n into n star is equal to n star n. If you prove norm n into n star minus n star into n converges to 0, then so we can say that n star equal to n star n, that is n is normal operator. So let us prove it. Norm n star minus n star n equal to norm n star minus nk into nk star plus nk into nk star. Okay, we have added nk into nk star and subtracted it also. So there is no change. And again we have added nk star into nk and subtracted nk star nk. So no change. Minus, this is not nk into nk, it should be n star n. Okay, so by triangle property of norm, here less or equal to nn star minus nk into nk star. Here norm nk into nk star minus nk star into nk, and this one plus nk star into nk minus n star n. It should be n star n. Equation 2. Since nk is normal, then nk into nk star equal to nk star into nk. Okay, so here this one 0, because nk into nk star equal to nk star into nk. Okay. So from 2 and 3, this is 2 and 3, we have norm of nn star minus n star n. This one less or equal to norm of nn star minus nk into nk star, this one 0, plus norm of nk star into nk minus n star n. Since nk converges to n and nk star converges to n star by equation 1. Okay, here nk converges to n and this proves that nk star also converges to n star. So we can write this nk star as n star and nk is n. Okay. So nk is n and nk star is n star. That is, both are same. Okay, that is, this is 0. And again nk star is n star and nk is n, that is, again this is same but different sign, that is 0. So from equation 1 and 4, norm nn star minus n star n converges to 0. That is, norm nn star minus n star n is equal to 0. And we know that norm x is equal to 0, that is, x is 0. So here this implies that nn star minus n star n is equal to 0. That is, nn star is equal to n star n. Hence, n is normal. Next theorem. The set of all normal operators on a Hilbert space H is closed subspace of Bh, which contains the set of all self-adjoint operators and is closed under scalar multiplication. Proof. Proof as this theorem. Okay. Let M be the set of all normal operators on a Hilbert space H. We first show that M is closed subspace of Ph. Let n be a limit point of M. We have to show that n belonging to M. Since n is a limit point of M, then there exists a sequence nk of distinct points of M such that nk converges to n as k tend to infinity. Okay. So here norm nk star minus n star. Okay. So as the explanation of theorem first, we can explain it as above. Theorem 1. So nk converges to n, then nk star converges to n star as k tend to infinity. And similarly, we can prove n into n star is equal to n star n as theorem first. Okay. So here nk converges to n and nk star converges to n star. Then right hand side of equation 8, that is, norm of nn star minus n star n tends to 0 as theorem first. Okay. This implies that nn star is n star n, providing that n belonging to M. Okay. Because here nk are the distinct points of M and n also is the element of M. This proves that M is closed subspace of Bh by property first. Okay. Every self-adjoint operator is normal. Therefore, M is closed subspace of Bh containing the set of all self-adjoint operators. To complete the proof, we have to show that M is closed under scalar multiplication. That is, if alpha is a scalar and n belonging to M, then alpha n belonging to M. This means that if n is normal, then alpha n is also normal for any scalar alpha. Since star of alpha n, that is adjoint of alpha n, equal to alpha bar into n star, because alpha t star is equal to alpha bar into t star. So star of alpha t equal to alpha bar into t star. So as per this definition, we can write star of alpha n is equal to alpha bar into n star. Since n is normal, we get n into n star is equal to n star n. So by equation 9, we have alpha n into star of alpha n, that is alpha n into alpha bar n star. This can be written as alpha into alpha bar into n star. Okay. Alpha into alpha bar, that is mod alpha square into n star. Similarly, star of alpha n into alpha n equal to, as per this definition, alpha bar into n star into alpha n. Again, this and this can be written as alpha bar into alpha into n star n, that is mod alpha square into n star. So from 11 and 12, alpha into star of alpha n equal to star of alpha n into alpha n, that is alpha n is a normal operator. Okay. This proves that if n is normal, then alpha n is also normal for any scalar alpha. Hence, n is closed with respect to the scalar multiplication. Next theorem. If n1 and n2 are normal operators on H with the property that either commutes with the adjoint of the other, then first n1 plus n2 and second n1 into n2 are normal. Let us prove it. Since n1 and n2 are normal, here given, so as per the definition of normal operator, it can be written as n1 into n1 star is equal to n1 star into n1, and n2 into n2 star is equal to n2 star into n2. From the hypothesis, either commutes with the adjoint of the other, that is n1 into n2 star is equal to n2 star into n1, because commutes with the adjoint of the other. Similarly, n2 into n1 star is equal to n1 star into n2. So let us prove n1 plus n2 and n1 into n2 are normal. To prove first, we have to show that n1 plus n2 is normal. That is n1 plus n2 into star of n1 plus n2 is equal to star of n1 plus n2 into n1 plus n2. Let us prove it. n1 plus n2 into star of n1 plus n2 equal to n1 plus n2. This can be written as n1 star plus n2 star. Okay, so multiplying this and this, we have n1 into n1 star plus n1 into n2 star plus n2 into n1 star plus n2 into n2 star. Okay, so by using 13 and 14 in equation 16, that is this property and this property we can use in this expression. So we have n1 into n1 star can be written as n1 star into n1 because n1 is normal operator. So here n1 into n1 star is n1 star into n1. We can write again n1 into n2 star. Here n1 into n2 star, that is n2 star n1. So we can write this one is n2 star n1. Similarly again this, as per this we can write this is n1 star into n2 and n2 star into n2 here, because n2 into n2 star is equal to n2 star n2. Okay, so we have this one here from first and third. Okay, so n1 star common, so we have n1 plus n2. Okay, and from here n2 star common, that is we have n1 plus n2. Okay, here again n1 plus n2 common. Okay, so this expression can be written as n1 star plus n2 star into n1 plus n2, and again this can be written as star of n1 plus n2 into n1 plus n2. Okay, so n1 plus n2 into star of n1 plus n2 equal to star of n1 plus n2 into n1 plus n2. Okay, we have this one, hence n1 plus n2 is normal. To prove second, to prove n1 n2 is normal operator, that is n1 n2 into star of n1 n2 equal to star of n1 n2 into n1 n2. So let us prove it now. n1 n2 into star of n1 n2 equal to n1 n2 into n2 star n1 star. Okay, so using the property T1 T2 star is equal to T2 star T1 star. Okay, so as per this property we can write this one as this. So here n1 into n2 into n2 star into n1 star. Okay, so from equation 13, okay, n2 star is equal to n2 star n2 because n2 is normal. So we can write this is n2 star as n2 star n2. Okay, so n1 and n1 star as. Again from 14 n1 n2 star is equal to n2 star n1 and n2 n1 star is equal to n1 star n2. So this can be written as n2 star n1 and this one is n1 star n2. So again using 13 n1 into n1 star as n1 star n1. Okay. So we have n2 star into n1 star into n1 into n2, and this can be written as per this definition, that is star of n1 n2 into n1 n2. This proves that this one, that is n1 n2 is normal. Next theorem. An operator T on a Hilbert space H is normal if and only if norm T star x equal to norm of Tx for every x in H. Here T is normal. Okay. So T is normal. We have the result Tt star is equal to T star T as per the definition. Okay. That is, this can be written as Tt star minus T star T is equal to O, that is 0 operator. Okay. We know that if T is 0 operator, then inner product of Tx x is equal to 0 or vice versa. So here T star minus T star T is equal to 0. So we can write this is inner product of Tt star minus T star T x, and x is equal to 0. So as per the additive property of inner product, this can be written as inner product of Tt star x and x minus inner product of T star T x, x is equal to 0. That is, inner product of Tt star x and x equal to inner product of T star T x and x. So that is applying the property T x y equal to x T star y. Okay. So applying this property, so we can write this is inner product of T star x and T star x. Okay. So in this also we can apply the same property. So this one as inner product of Tx and star of T star, that is T double star. Okay. So we know that T double star is equal to T. So here it should be T double star, and T double star is T, that is T here. And again apply the property inner product of x equal to norm x square. Okay. So as per this property, this can be written as norm of the T star x square is equal to norm of Tx square. Taking the square root of both sides, that is norm of T star x is equal to norm Tx for all x belonging to H. So it is proved. Next theorem. If n is a normal operator on a Hilbert space H, then norm n square is equal to square of norm n. So let us prove it. We know that if T is normal operator on H, then norm Tx is equal to norm T star x. So now replacing T by n and x by nx. In equation 1, we get norm of n into nx equal to norm n star nx by equation 1, because here norm Tx is equal to norm T star x. So suppose nx as vector and n is operator. So as per this definition, we can write this is norm n star nx. So this norm of n square x equal to norm of n star nx. We can multiply or divide by any scalar of both sides. Okay. Now we divide equation 2 by norm x. Okay, norm x as a scalar. So dividing this by norm x and using this property, that is norm tx upon norm x as norm t. So if you divide both sides of norm x this equation and taking the supremum of both sides, then this can be written as norm n square and this one can be written as norm n star n by this definition. Already we have proved norm t star t is equal to square of t. So this can be written as norm n square. So here we have proved norm n square is equal to square of norm n. In this lecture, we have discussed the normal operator and its properties. These are the references which have been used in this lecture. First, function analysis, Dover publications, written by George Beckman and Lawrence Naresy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.